period 3 oxides. If you take a look at the period 3 oxides, these are the various oxidation states that we have. And in the case of phosphorus, you can have 2, which is actually +3 +5. In the case of sulfur, +4 +6. And your chlorine could be +1 +7. And obviously, your chlorine could display a variety of oxidation state from -1 all the way to +7. So for period 3 oxides, the one in bold are the one that's needed for your A-level. So it's just namely these 6 of them. All right. So let's take a look at the chemical bonding. For all the first 3 oxides, they are all giant ionic. Silicon dioxide is again giant molecular lattice structure, similar to silicon earlier. And the rest of the other oxides are in fact simple molecular. So in terms of the nature of the oxides, as we all learned at O-level, all metal oxides are supposed to be basic and ionic. In this case, sodium and magnesium fulfill that description. For aluminum oxide, is amphoteric. And bear in mind that it is an ionic compound, though it does display covalent character, primarily because your Al3+ has extremely high charge density that's able to polarize the electron cloud of the anion. But predominantly, aluminum oxide is still ionic. From silicon dioxide onwards, they are all non-metal oxides, and if you're non-metal oxides, you are covalent oxides, and obviously you are going to be acidic. Reaction with water. In the reaction with water, later we'll take a look at the equations. Let me take through in terms of the observations first. Reaction with water, sodium oxide dissolves very well with water to produce sodium hydroxide, and that is a strong alkaline, so pH is around 13. Magnesium oxide dissolves poorly with cold water, and the pH is approximately about 9, though it dissolves pretty well when the water is hot. Aluminum oxide does not dissolve in water, pH 7. Silicon dioxide does not dissolve in water, pH 7 as well. P4O10 dissolves in water to form H3PO4, while SO3 dissolves in water to form H2SO4. All these solutions acidic, so pH 1 to 2 because strong acids is formed. And for the case of oxides of chlorine, they will be able to produce all these acid, but like we noted, these are not in the syllabus. In terms of states of the oxides, bear in mind that all those that are giant ionic or giant molecular are all definitely solid. However, in the case of P4O10, it is solid because of the large number of electrons that it has and the relatively strong instantaneous dipole-to-dipole attraction forces that arises from its electron cloud. In the case of SO3, it's a gas. Let's take a look at now the equations. For the equations, we can see that these are equations that you need to be able to know. But one broad sweeping statement we can tell you is that this, that's the case of chlorine oxide, which is, by the way, not in the syllabus. All the reactions are in fact non-redox. You can check that in terms of the oxidation state. P4O6, if it does dissolve in water, it still forms a phosphorus with an oxidation state of +3. In the case of P4O10, it's +5, and H3PO4 is also +5 as well. SO2 is +4, and when you form an acid, it's from sulfurous acid, which is your H2SO3, oxidation state also +4. Sulfur trioxide, which is actually +6, and H2SO4 +6 as well. Important for us to highlight that the H3PO4 is in actual fact dibasic. That is actually its structure. Bear in mind that that's how the displayed formula looks like. So you actually only have 2 hydrogen that's primarily bonded to oxygen, which makes them electron deficient. So these 2 hydrogen are the one that makes this compound dibasic and not tribasic actually. So that's always a common misconception. So therefore, because of that, in terms of number of moles of sodium hydroxide that can neutralize this, remember it's just 2 moles. So relative comparison indicates that H3PO4 would have 3 hydrogen bonded to oxygen. So these 3 hydrogen will be electron deficient and could be loose as H+. As a consequence, your H3PO4 is tribasic. Both H2SO3 and H2SO4 are both dibasic. Finally, for this portion, we want to highlight that aluminum oxide, which is amphoteric, will be able to dissolve in sodium hydroxide, giving all the various forms of your complex ion of your aluminum. So bear this in mind. The last part to highlight is to take note that actually silicon dioxide, although cannot dissolve in dilute aqueous NaOH, it can dissolve in fused or concentrated sodium hydroxide to produce actually a silicate. This was a reaction that you do learn at O-level, and at A-level they did test once before, asking you to write a balance equation for this.